Hi, let's get into some specific examples of how to classify extrema using the first derivative test. You should have already looked at the introductory video where we talk about what extrema are, and here I'm referring to relative maximums, relative minimums, and then the third type of critical point, horizontal point of inflection, and the first derivative test, which is a way to determine whether it's a min or a max or an HPI, depending on whether or not the derivative changes sign, and if so, in which way. Did you know what I meant by that? If not, go watch the other video. And now, if you do know what I mean, let's get into an example. Okay, so let's say that I gave you this cubic function. F of x is x cubed over 3 minus x squared over 2 minus 6x. The question at hand right now is locate and classify all of the critical points. Alright, now here I've already drawn a picture of f of x, and if you want, actually I really encourage you to do so, please get out your graphing calculator and make sure that you can get a nice solid picture that looks like my picture right here of the function in question. If you get a picture of the function, you can already see the answer to the question. The question is, where's all the critical points, first of all? Remember, those are places where either the derivative is equal to 0 or the derivative does not exist. And you can see the derivative is equal to 0 right at the top of this hill right here and right at the bottom of this trough right here. Alright, so those are our two critical points. And classify them, well, that's easy to see if you give me a picture. This one's a max because the highest thing around. This one's a min because it's the lowest thing around. Okay, so if only we knew the x, y coordinates to both of these points, this is what we don't know right now. If only we knew exactly what the xy coordinates were to those points, we'd have the answer to the question. Now, don't just zoom in on the graph. That's not going to get you points in my class. You're going to use calculus to locate and classify all of these critical points. Okay, so now I'm going to show you a classic four-step method that is going to get this question done for you. Step 1 is, of course, take the derivative. You're not going to be able to locate the locate the critical values in step 2 unless you have a functional form for the derivative. Okay, so let's all do step 1 together, and please play along with me. Here's the function right here. Write down what the derivative of this function is. I hope you tried to do that, because I'll tell you, sometimes when I give out this function on a quiz or test, I see students trying to apply the quotient rule. Did you use the quotient rule on this first term, x cubed over 3? I really hope not. Now you could have, because it is a quotient, it's divided by 3, but really, as long as there's no x's on the bottom, what you want to see this as is the constant multiple 1/3 times the power function x cubed, and just use the power rule. You do not need to use the quotient rule if you don't have any x's on the bottom. This is just a constant multiple. Alright, so keep that in mind. If you did use the quotient rule, try to retake it again now just using the power rule, because learning how to do it that way is going to save you a lot of time and headaches. Alright, so then power ruling that first term right there, the 3 comes down and it knocks out the 1/3, cancels it out, and we get an x squared. Likewise, on the middle term, the 2 comes down and it cancels with the 1/2, so we just get a minus x to the first power. Last term, minus 6x, just turns into minus 6. Step 1 is done. You just need to get the derivative. Alright, step 2 is when we're going to find the critical values. Now, as you'll see, in case you do some of the homework assignments, you'll see the word critical value is a little bit different than the word critical point, okay? The technical difference between critical value and critical point is that critical values are simply the x values where the derivative either equals 0 or it does not exist. Just the x values. The critical points that they ask you for later is going to be literally the x, y points. So the critical value is the x value, and then you plug that into the original function to get the y value, and that's going to be the x, y point for the critical point. Alright, so by the end of this, we're going to answer our question at x comma y equals what? The x and y values. So step 2, we're just going to get the x values first, and what we're going to do is we're going to take the derivative, and we're going to set it equal to 0. Now keep in mind, critical values of x are defined as places where either the derivative equals 0 or it does not exist. So that does not exist part has to do with if you have a function where maybe something can go wrong in the function. So let's say that I had a fraction with x's on the bottom. I wouldn't want to divide by 0, right? That would be outside the domain. And if I divided by 0 in the f prime, then it would not exist. All right? Another thing that can go wrong is square rooting a negative number. So if I had a square root term inside the derivative, I'd have to consider places where that square root term would try to root a negative number, and those would be places outside of the domain, not in the domain, and so the derivative would not exist at those points. That's how you would deal with does not exist, but what kind of function do we have for our f prime in this example? What? Polynomial? Did you say polynomial? Great. Exactly, polynomial. And what's the domain on polynomials? All real numbers? Excellent job. I'm glad you remember that from pre-calculus. The domain is all real numbers, which is to say there's no possible way that for any x value in the reals, the derivative cannot exist. If I plug in a number, I'll get a number. And so I'm only left with this first stipulation. When is it equal to 0? So I set it equal to 0 here. What do you want to do? Quadratic formula? Factoring? Hey, it's either way at this point, but hopefully you're seeing this as something that you have a chance at factoring because that is a little faster and less prone to mistakes. So you might want to try to factor this out right now, and you would hopefully get x minus 3, x plus 2. And if you're not sure if that's true, just go ahead and refoil it out and you'll see that that is definitely true. Or you could use the quadratic formula. Alright, so either way we're going to conclude that the critical values are where x is equal to minus 2 or x is equal to 3. Alright, so here in this bubble right here, we have the critical values, but we don't have the critical points yet because we haven't taken each value and plugged it back into the original function in order to get the xy point. So that xy point will be the answer in step 4. Alright, so it looks like we're about halfway done. Got the derivative, set it equal to 0, found those critical values. Now we're going to draw the f prime sign number line, and then later in step 4 we're going to classify each of those critical points as a min, max, or HPI, and we'll have to fill in the little detail of what the y coordinate was. Remember, we haven't yet found the y coordinates for each one of our critical values. Alright, so let's just move on to f prime sign number line. And remember, this is just a one-dimensional number line that describes values of x. Here, we've got two special critical values. One is located at -2, another is located at 3. Now at this point, I would like you to try to resist the urge of doing this. I see this all the time. What's wrong with that? Why can't I tick off 0? I always like to mark off where 0 is. It's misleading. In this case, when we draw the f prime sign number line, we're trying to separate the number line into different regions of either the derivative being positive or negative, and those regions are going to be separated, must be separated, by the places where the derivative equaled 0. Alright, now, was x equals 0 one of the solutions to this equation? No, it wasn't. So x equals 0 is not a critical point. So I can't stress this enough. Only tick off the actual critical values of x on the f prime sign number line. Do not put the 0 in there just because you like to see where 0 is, because that's misleading and it makes you think that x equals 0 was one of the critical values, which in fact it's not. And if you go over here and you see what the function's doing at x equals 0, it's not a max, it's not a min, it's not an HPI. It's just a regular old point where the function's decreasing. Alright, so you don't want to do that because if you take off the 0, then you're going to have 1, 2, 3, 4 regions to deal with. Here, we only have 3 regions to deal with. Okay? Our f prime sign number line will be complete after we've firstly ticked off each of the critical values, and then secondly, determines the sign of the derivative inside each of the different regions that are created separately by these tick marks. Alright? So let's deal with these regions one at a time. The first region over here is when x is less than -2. Now because I know this is a place right here where the derivative equals 0, then it must have one sign, either positive or negative, for every value of x inside this region over here. Okay? So that means that I can use any value where x is less than -2 over here as a test point to see if I will get a negative or a positive value out of the f prime sign number line. Alright, so you guys know we're in step 3. I'm going to erase the instructions so I have a little more room here. What I'm saying is, in each one of these regions, we must use a test point, a value for x that satisfies, in this case, x is less than minus 2. In this case, x is between minus 2 and 3. In this case, x is greater than 3. All right, any point you like where x is less than minus 2, you throw it into the derivative and you see what the sign of the derivative is, okay? So for this test point right here, let's say I'm going to use the test point x equals minus 3. Minus 3 is less than 2. So is minus 1,000,000. So is minus 2.5. Any number that satisfies this inequality can be used as a test point here. And what I mean by test is we're testing the sign of the derivative. So that's why we're going to take the chosen test point value and plug it into the derivative and see what we get. All right, minus 3 is minus 6. Minus 3 plus 2 is minus 1. So that's minus 3 times minus 1. Are you guys following this? Oh, sorry, that's minus 6. If you are, you saw that mistake. All right, so what is the value of the derivative at my test point x equals minus 3? The conclusion is f prime of minus 3 is equal to 6. You see my computation right here. I took my chosen test point, which you can choose whatever you want, as long as it satisfies that, put it in the derivative, and you see the value of the derivative coming out as positive 6. That means when x is equal to minus 3, the derivative is positive. And because I know it does not change sign inside this region, because it can't change sign unless it hits 0, which it does right here, I can conclude that it's always positive for every value of x inside that region. Alright, so that's easy enough. You pick whatever test point you want. Okay, so if you understood that, I'm going to erase that so I can go into the next region here. And once again, I'm going to choose a test point. Now the test point for this middle region must satisfy this inequality right here, which is to say my test point will be between minus 2 and 3. What number will we choose? 0, 1, 2, minus 1. Any point you want that satisfies that, okay? So in the middle here, I'm going to choose my test point x is equal to 0. And once again, I'm plugging that test point into the derivative. And that will give me the sign of the derivative for all values of x in that region. 0 minus 3 times 0 plus 2 is minus 3 times 2, which is minus 6. So the derivative of 0 is minus 6. That's a negative number. And then because what I know about functions, I can conclude that all of these are going to result in negative, negative, negative values, because there's no way they could change to positive without hitting 0. And that's what they do here and here. Alright, so that's logic for you. I've made my conclusion that's negative in that region. And then we just got the one more region to finish with. Alright, so I'm going to erase that so it's not confusing with the other region. Over here, I have to pick a point where x is greater than 3. So I'm going to take my test point right here. Maybe x is equal to 4. Did you want to use 5? Go ahead, use 5. Did you want to use 4,500? You can. It doesn't matter as long as it satisfies that. Sometimes it's easier when you're out in regions like this to use like a huge number, because you don't actually even have to calculate the number. You just have to understand, like, is it going to be positive or negative? Like, for example, I don't want to use a test point 4. You already saw me use normal test points enough. Let me use a test point, what is that, 100,000? Sure, whatever. I'm going to take the number 100,000 just in my head and throw it into the derivative. This is a statement of the derivative as well as this. This is a factored statement of the derivative. Now if I took the number 100,000 and put it in here, 100,000 squared, that's huge. Minus 100,000, well, that didn't really make a dent compared to 100,000 squared. And neither did minus 6. So I know this is going to be a big number, and it's going to be really positive. F prime of this huge number is going to be greater than 0 for sure. Just because I know 100,000 squared is just way bigger than either 100,000 or 6. Alright, so that's me just eyeballing it. And you can do that too, as long as you're in a region where it's okay to pick a crazy number. Notice over here, that wasn't okay. Alright, so that works in far off negative regions or far off positive regions. Either way you slice it, or if you are more comfortable using a normal test point like 4 and actually plugging it in, I think you'll conclude that the derivative, if you put a 4 here, is going to be positive 6, and that's a positive number 2. Any way you slice it, we get the conclusion for the f prime sign number line in step number 3. The f prime sign number line. Conclusion. It turns from positive to negative to positive again. And so now let's go on with step 4. Step 4 is going to be classifying it, and also, if requested by whoever's asking you this crazy stuff, if requested to get the actual xy points, you would also do that in step 4. Okay? So I'll do both of those things. Alright, step 4. Now, do not look at your notes. Try to rediscover the first derivative test every time you use it. That way you'll never have to memorize it. Okay? Let's rediscover it from picturing what we know about functions. The function is increasing, and then it hits 0 at minus 2, and then it's decreasing. And what kind of relative extrema is that? Goes up, hits a peak, goes back down again. This is a max. X equals minus 2. That's a max right there. Alright, and the same logic on the other one is going down, and then it hits some rock bottom, and then it goes back up again. Okay, so that's a min. So this one over here, x equals 3, that's going to be a min. And there you go. That's what I call classifying extrema. Now if I happen to, as I will in the next example, have it where it doesn't change sign at all, let's say it was a plus, hit 0, then it was a plus again, do you remember what that would classify as? Horizontal point of inflection, that's right, HPI. We don't have any of those in this example. Okay, so now to finish off the question, if someone actually asked me for what are the critical points, then additionally in step 4, in addition to classifying it as a max, I would have to say, well, x is equal to minus 2. Oh yeah, that looks like what I saw in the picture. Sweet, I'm getting it right. Hey look, x is equal to 3. Oh nice, that's what I saw on my graph in my graphing calculator. Yes, I'm doing it. But then I haven't yet answered what are the y's. So let me show you how you do that. And this is a little part of step 4 if it was asked for. X equals minus 2, I have to find out what f of minus 2 is, okay? Because they're asking me for the xy point, right? So then I have to take the minus 2 and plug it in here, and I would get 1/3 of the quantity minus 2 cubed, minus 1/2 of minus 2 squared, minus 6 times minus 2. And what's all that equal to? Did I get a number here? I think I got the number 16 over 3. Is that what you got? 16 over 3. All right. So this is where it gets a little confusing, kind of like equation of the tangent line problem. What do I plug it into? F or F prime? Let's look at the steps again. Step 2, you're looking at F prime equals 0. Step 3, you're plugging in test points into F prime because it's an F prime sign number line. Step 4, if they ask you for the xy critical point, that's when you plug it into the original function, not the derivative, because they're asking you for the xy point. And that's how I can draw the conclusion that this is a max, this is a relative max, and it's located at -2, 16 over 3. Okay? So this is the point in step 4, where if you're asked for the xy point, then you have to make your conclusion. Alright, and so go ahead and do that for the other point where x was equal to 3. When x equals 3, what is y equal to? What is f of 3? So you plug in the number 3 there, and you should get the number -18. And this is where a graph is just so relieving, because if you've had a graph of the function the whole time, not only are you seeing some nice agreement, hopefully, with what you saw on there, but you've also been able to check your step in the middle, because when you found the critical values for x over here, you were able to reconcile that with the places where you located extrema in the picture. Alright, can't stress that enough. If you have a graphing calculator, use it, and use it to follow along with your algebraic work. Okay, so let's get into one more little example, and I'll have a whole separate video of applications to business examples, in case you're wondering where those are. In this next example, I'm going to give you a function where the derivative does not exist. So let's see if you can recognize that. And the question is the same question. I want you to locate and classify all the critical points. And the function is the cube root of x. Same question. Locate and classify all the critical points on the cube root of x. Okay, so the first thing I'm going to do is graph that function just to make sure I can get a feel for it. And it looks like that function looks like this. Hopefully you've got something where the function looks like that. Now, if I said locate and classify all critical points, do you see any mins? Do you see any maxes? So at first I'm like, what's the deal with this? It doesn't even have any critical points. But actually, turns out what we're going to have is we're going to have the example where it does not exist. Okay, so how are you going to take the derivative of this function for step 1? Step 1, find the f prime. Let's see what you do. Are you thinking about rewriting that function in fractional powers? I hope so, because that was the answer. That was what I'm looking for, and if you weren't thinking that, that's a hint. Take that function, cube root of x, rewrite it in terms of fractional powers. That way the step 1's going to be a lot easier. What is this? X to the what? X to the 1/3. This is a power function, but unless you rewrite it in terms of its fractional power, you're not going to have a good time trying to take its derivative. Okay, but anyway, I see it right there, so now let me just go over to step 1. What is f prime of x if f of x is equal to x to the 1/3? Just normal old power rule, so that's going to be 1/3 x to the what? What's 1/3 minus a whole 1? 1/3 minus, that's negative 2/3. Okay? Alright, now the step 2 was going to be to find the places where this either equals 0 or does not exist. Locate the critical points. Critical points are defined as either places where the derivative is 0 or it does not exist. Are you having a little trouble with this? You might be, because you see, sometimes it's easier to look at functions in this way versus that, like for taking the derivative. But then sometimes it's easier to look at functions like this. Did you rewrite it like that? Sometimes it's easier to look at functions inside of the way that they are in a fraction, because then when you're solving them equal to 0, you can kind of think of which way to go. Okay? So that's how I was actually looking for you guys to solve it, is first to rewrite it as 1/3 of the cube root of the quantity x squared, and then you set that equal to 0. Now, do you know how to solve something like this? If you have a fraction that's equal to 0, in general, all you have to do is find where the numerator equals 0. A fraction will not equal 0 unless its numerator equals 0. Okay, so when does the numerator, the stuff on top, equal to 0? Numerator, I don't know. Well, the numerator is 1, okay? So are you asking me when 1 equals 0? Because that's never true. And that's the answer. This is never going to equal 0. If you graph it, you'll see that it has no x-intercepts, which is the same thing as saying that the output of this function will never be equal to 0. So the answer is never. Never. Why? Because the numerator 1 does not equal 0 for any values of x. Okay? So does that mean there's no critical points? No, it just means that there's no critical points in the sense of equaling 0. Now, is there any place on this function, any values of x, where this function would not exist? Am I going to do something wrong here? Divide by 0, right? If x is equal to 0, then it does not exist, right? Because that's a divide by 0. Okay, so just to review a little pre-calculus skills here, if you get caught up with a fraction and you want it to equal 0, the numerator has to equal 0. If you have a fraction and you want to wonder when does it not exist, that's when the denominator equals 0. Okay, so with fractions, you are separately considering two questions. Can the numerator equal 0? or can the denominator equal 0? All right, and in this case, the second question right here is the only thing that yields a critical point, so x equals 0 is a critical point. All right, let's go on to step 4. Step 4 is the f prime sign number line. Or sorry, step 3. Step 3 is the f prime sign number line. Okay, and I'm actually for step 3 going to do the f prime sign number line right below the function so we can make sure that we see the agreement between what we're seeing here and what we observe in the behavior of the function. Remember, the derivative sign describes whether the function is increasing or decreasing. So another way, an alternative way besides plugging in test points that I could fill out this f prime sign number line is if I have the original graph, I could ask myself, is this increasing or is it decreasing? All right, so let me go ahead and ask myself, let's see, is this function look like it's going up, increasing, or going down, decreasing? Looks like it's going up, right? And if you drew the slope of the tangent line or looked at the tangent line at any point where x is less than 0, you would see that tangent line has a positive slope. If you use the test point, you would also get that the value of the derivative is a positive number. So let me show you that alternative way. We have 2 ways to fill out in step 3 the f prime sign number line. Looking at a graph and seeing if it's increasing or decreasing. And also, you probably want to do both ways, make sure you're always 100% correct, plugging in the test points. All right? What's a good test point to use for this region? X equals -1? Yeah, sure, why not? So let's try to get the f prime of the number -1. That's 1 over 3 cube root of the number -1 squared. All right, and remember, you can cube root negative numbers. They come out negative. You can't square root a negative, or you can't do any even root, but odd power roots are possible over the negative reals. And anyway, that doesn't matter because the quantity squared in here squares away the negative. So the cube root of 1 is 1, so that's equal to 1/3. And sure enough, 1/3 is a positive number, and so I've got 2 different ways to make sure I filled this out right. I hope you use both. Okay, so likewise, you will find whether you use a test point of x equals 1 or 100,000 million, or you just observe that the graph of the original function is increasing or going up, you can state on your f prime sign number line that you have all positive values there. Okay, and so the last part is going to be step 4, where you're going to classify. And remember that I told you there's 3 possibilities. Either f prime changes from plus to minus, or minus to plus, or third possibility, it doesn't change at all. Looks like it doesn't change at all, right? So usually I would classify this as an HPI. I would take that as an answer, horizontal point of inflection. The only thing is, when you actually look at this function, it doesn't look like the plateau as we've described it in the normal way. It's actually more of a VPI, vertical point of inflection, because you see it's like a vertical plateau. All right? Now, if you graph this function, you may not even notice that the derivative does not exist at x equals 0. You might think that's fine, but actually, let me show you with the green marker what happens to the tangent line. The tangent line is slightly positive, then it becomes more positive, then it becomes more and more positive. Right here, the tangent line is literally vertical. Okay, so like, what would I say is the slope of this vertical line? Infinity, minus infinity, something like that. It does not exist, okay? So that's why, because of the vertical tangency at the point x equals 0, that's why it's a critical set point in the sense that the f prime does not exist. All right, and then once again, it starts to top out in a normal way and just have a positive slope on the tangent line. Alright, so classify it as an HPI, that's fine, I would take that answer, but it's really a little bit more like a VPI because it's a vertical place of inflection. And the main thing that I want you to take away from that is if the derivative doesn't change sign, it's neither a max nor a min. When we get into the applications video next, you're going to see how valuable it is in terms of business to be able to locate maximum and minimum points on your graph using calculus. That's what we call optimization.